So welcome to another stream. We're going to talk today about getting the most recent value out of your Postgres database. And really everything we're going to talk about today, with one exception, can be done in Postgres. This is not specific to Timescale in most cases. What makes it specific is that, time series data, this is such a common operation, right? I feel like on these streams or elsewhere, I've told this story often, and we see this in Slack time and again in our community channel because it's such a common need. In my previous life, before coming to Timescale, I worked at a company that made these little sensors, and my little view of things is over here, so that's why I'm glancing over here. I guess I don't need this because I can't hear any audio, so I'll just take it out. And so, we had literally hundreds of thousands of these throughout the world reporting data in, and they were grouped by, maybe accounts. So we had multiple customers, and a customer might have, 3,000 or 10,000 or whatever that was. And so in our application interface, one of the most common things that we needed to know, so we had a whole staff of, they still do. I say we have, I mean, it's something that others, the company still exists. Had a whole staff of analysts. And every morning, like one of the first things that they would do, we'd had automated reports and other things to say, when is the last time these devices reported in? Because they would report maybe once a minute, once every 5 minutes, once every 10 minutes. And if it wasn't reporting, that was a big problem because they were monitoring machines. And if it's not reporting, we can't monitor the machine. And so we needed to, just have that identity. And so really there are so many ways to go about it. But if you're not thinking about it, in terms of your database and what's going on, you might end up just trying to do like a select on your table that might have billions of rows, right? And so depending on how you approach that with Postgres, you can get a really underperforming query when it doesn't have to be. And there are multiple ways to go about this. So I've now said this for 3 or 4 streams in a row. I'm actually not planning to do much by way of slides. Hopefully it's just a pretty straightforward run through some SQL to give you some ideas, and I'll point you to a web page at the end, just to kind of get you thinking some more. There are certainly, I have at least 4 options. There are probably more than that, but these are ways to get you going. So let me get my screen in here. I'm going to do my best to, nope, that's not what I meant to do. I had to I was able to go actually attend a live event not long ago, 2 weeks ago in New York, the Postgres Conf NYC. It was great. I was able to give a talk, but I realized some of my settings are still set to demonstrate from there. So here's what we're going to talk about today. Are you going to come on? There we go. And I'll put myself over here. That tends to be, I think, generally the right deal. I'm realizing my background isn't very cool. So let's see if we can get a good background in here. There, I like that background. So retrieving the last point value. So that's the topic of today's conversation. And again, start a few minutes late, mostly because my internet went out like 3 minutes before the stream started. So I think we're stable and hopefully working out well. So here's what we're going to talk about today. If I can get my mouse over here, we're going to talk about what a last point query is. That's generally what we're talking about. What is the last stored value for a thing? And so in most cases, this is a time value. In a sense, there's a distinct part of this that we'll talk about, which actually could be any table. It doesn't necessarily have to be a time-based thing, but again, usually if you have multiple entries for something in a table, usually that means in some way you are measuring something over time, at least. So what it is, and then here are the 4 options we're going to talk about. Lateral join, which is very typical. Again, if you're new to Postgres, lateral might be a new thing for you, and you've tried other ways to figure this out. Hopefully this is a more straightforward way. We'll talk about 1 or 2 things with it. Recursive CTE. So CTE stands for Common Table Expression. And again, I'll show you briefly what that is. And the recursive nature of it allows it to query itself. That's what makes it recursive. And so it's kind of like working down through a tree. Now, I'll be honest, recursive queries can be challenging to use if you're not careful. And so we're going to look at what that might look like. Um, let's see. Timescale SkipScan. So this addresses that need. A lot of people would love to do, and this has been a need for a long time, and not many databases actually support this. The nature of something like I have this big table that has lots and lots of readings, but I have a good index, but still when I select distinct something with just those columns, for some reason, Postgres doesn't just find the most recent distinct values, even though things are ordered correctly. And so we're going to look at what that might be. And finally, a logging table, which it really is a good application design opportunity, regardless of what these other options. There's just going to be situations. It could be simply a throughput it's where you really need to consider doing a separate, kind of like a last point table that just tracks that last entry. So it's a much smaller table and easy to log. So my goal here is I'm going to put these slides up. I have not been doing a good job with this because I get so excited about talking about what we're doing, so that I can see these as I go back and watch the video to put correct markers for the YouTube after this. So let's go ahead and get started. If you have any questions, put them in the chat. I'm doing my best to watch the chat. And if you happen to be watching this after the stream on YouTube, there should be links in the description to a couple of the web pages that I'll show. They're in our docs. And then also links to various points in this. So maybe you don't need to know, what a last point query is, or what the first set of queries a lateral join is, but you'd like to talk about SkipScan. You should be able to click the link to that timestamp and get to that point of the video. So if you haven't already, and you are watching this after the fact, or right now, if you're on YouTube or Twitch, please subscribe. We are doing these streams multiple times a week. We're going to take a break over the holidays here. In the beginning of the year, we're going to reassess and see if these are the right shows, if we need to do something a little bit different, but please subscribe and keep updated. All right, so let's do this. What is the last point query? So we actually talk about this in our docs, and I moved away from the doc I wanted, and I knew I was going to do that. So let's do this. We'll go to docs. Love all my tabs. When my internet went out, I got frazzled here, so I actually don't know where I put everything. But let's go to under how-to guides. We have this section called querying data, and under advanced analytics, there's lots of examples here. Some specific to Timescale, and some not. Some of this is just Postgres functionality, ways to get various things. Cumulative sum, rate, delta. Then there's some time bucket, functions first, last, histogram, blah blah blah. Go to the very bottom of this page, and we have the section on last point. So actually, we've updated this recently, and I will show you 3 of the 4 things referenced here. We actually haven't updated this, and I realized that in preparing for the stream yesterday, that we haven't updated this yet for SkipScan, so we need to do that. So I'm actually going to just follow this kind of table layout because it's just kind of easy, to be honest with you. I'll show you how I created the tables, and we are about to, in the beginning of the year, we will start to make the SQL from the streams available on GitHub. We just haven't been doing a great job coalescing them as a team, and we're working on that right now. So I will try and get these up into a repository sometime soon. But certainly at the beginning of the year, we'll make an announcement, and you can go find these, or slow down and pause if you need to, or reach out to me in Slack. Join our Slack community, and we'll make sure we can get these to you. So we'll talk about our setup, but this is where you can kind of get the overview, right? So we talk about you have this. You're tracking an item, in this case, a truck or a vehicle. I use truck because it's easier to type for me. Tracking a truck, it has some properties, and then you have another table where you're tracking readings about this thing. So in this case, it's a truck, right? It could be a truck. This is magnetic. That's why I keep reaching under my desk. It could be one of these things that's spitting, saving into your database, 100 values every minute, right? Whatever that is, you have this table that's storing some metric data of some sort. So in this case, we're just tracking a fake latitude and longitude for a truck. And basically, I have a script, a job running, which we'll talk about that too, in Timescale every minute, and it's just creating one new reading for each truck every minute, or most trucks every minute. I'll explain that too. So we have that table, and one of the things we often need to do is say, for every truck or for this set of trucks, get me the last recorded value in that table. And as that table grows, often that query gets slower if you don't have the right query approach, the right indexes, or the right table approach, schema approach. So let's talk about it. So that's what last point is. For each item of the thing I'm measuring, I'm tracking what is the most recent set of values or most recent value based on time. All right. Now, one of the things this is how my brain works. I'm playing lots of things, and I realize I should have pulled this up. We talk about this often. This is a blog post on the SkipScan stuff, which again, I'll make sure there's a link in the description. This is on our blog. We released this back in May in TimescaleDB 2.3. And so SkipScan, I'll show you how that works as we go through the SQL. But we talk about this, and the last point, I feel like I've brought this up a few times here, not to, and Jill's gonna, she's gonna love me. I'm coming up with all kinds of blog posts that I should have had links for ahead of time, and I didn't, because that's how my brain works here. Anytime we do benchmark, the one thing that most time series databases, we have this tool called TSBS. I don't even care about what this is. This happens to be ClickHouse. This has nothing to do about this benchmark. One of the queries we do often make a fairly big point about, however, is this last point query. And you'll notice that it is the one query that is significantly better, and it is for most OLTP databases. So that's a transactional database, Postgres, SQL Server, MySQL, Oracle, things that can be indexed appropriately. An index on any column generally can work more quickly under the right circumstances. And so that's something that you need to know about and recognize. That's why we bring it up. It's such a common query for time series data, and yet not every time series database can do it as well. And that's just the nature of how things work. All right, so let's look at the first option, lateral join. So actually, as I do that, let's talk about the setup of this table. So this is a database called last point. To start with, I have two tables, and I've already done this work. So I created a trucks table. It just tracks, a make, a model, and a weight class, just random values I made up. You'll see in a second. And then a location table that has a timestamp, has a truck ID, and then a fake latitude and longitude value. They are realistic as long as they are within the state of Pennsylvania. So I am in Pennsylvania in the US, and so I'm generating random latitude and longitude numbers within the bounds of Pennsylvania. That's it. All right. I made that truck location table a hypertable. So I am using timescale functionality for this. That is not necessary for finding the last point. Now, there are things we do within timescale that can make this more efficient. And so if you're using time series data within Postgres, we would always encourage you to consider using timescale and our hyperfunction and hypertable functionality. All right, I inserted 105, so follow along with me here. 105 fake trucks for this data. And I'll just free this up a little bit to give ourselves a little bit more space. So 105 fake trucks, and they look like this. So let's go ahead and select it out. I meant to do that, not delete. So let's say select star from trucks. And so it's just random data, truck IDs, randomly selected a make, a model, and a weight class. And that's it. All right. And then I created a couple functions, and these are just helper functions. One allowed me to create a random array of data. I'll show you why I did that in a second. And then another one, I've demonstrated this in videos previously about generating fake data with generate series. So probably another link I need to put in the description below. So we'll do that. There's a series of videos I have done on that and blog posts that we've worked on. So this comes from that. Just allows me to get a random value between 2 points, a high and a low. And so I'm using this to generate fake latitude and longitude values. That's it. That look a little bit more realistic. And then what I did is I inserted into that location ID a month's worth of data. So generate series now minus 4 weeks up to now in 1-minute intervals. So for every truck, 105 of them, I generated 1-minute readings for 4 weeks of time. All right. That equated to a little bit more than 4 million rows. Let's see how many are in there now. Yeah, a little over 4 million rows. All right. So it's not a huge table, but it's enough to allow me to show you how to do this work. Now, why did I do 105 and not 100 or something even? Well, what I did then is and so that should have equated to about 4 chunks. There's actually 5 chunks in here. So again, a hypertable, we take care when you create a hypertable and you insert data into it based on time, we take care of partitioning that table under the covers, which can make a lot of things more efficient. Obviously, if you have a lot of time series data, you can manage the size of those chunks and so forth. A lot of things to discuss that we can talk about there and we have in other videos and other blog posts and so forth. So I expected 4, and hopefully I'll get to that in a few minutes, why I wanted to have multiple. Now, what I did, I chose 105 for this reason. I wanted to be able to show, if all of the values are recent until now, it's hard to demonstrate what I want to show you. What happens when that truck or that device doesn't report for some period of time? And so for trucks 101 through 105, I just deleted random periods of data further back in time. So truck 101 has data up to about a week ago, and truck 102 has data up to about 2 weeks ago. And I just did that so that we could see, that when you do this kind of selection, you're trying to find the most recent value for every item. If the indexes and so forth are set up correctly, this should still generally be pretty fast. But there are situations where it might not be, and that can dictate a different schema or application architecture. So, and then how many readings do we have? So for most trucks, we have, a little over 40,000 readings for the month. You'll see that those special ones up here start to decline over time, right? So truck 101 only has 30,000. Truck 102 only has 20,000. So the fewer number isn't necessarily what I'm trying to demonstrate. That just shows you that they stopped reporting further back in time, and therefore, the index and the way that Postgres might have to go find that information, even on a partitioned table, is going to be impacted. And so, depending on how you treat that, it might be an issue. All right. So, what is the first way to do this? The first way to do this, and I think I had already done that, but boom, one more time, is a lateral join. And so a lateral join is a special, I'm going to see if I can make this just slightly bigger to get it on the screen over here. A lateral join, in fact, since it's in the upper left, I'm going to do this just to make sure it's as big as possible. There we go. So what a lateral join does, now if you're new to Postgres, that lateral might be a new thing for you. So I've said often my background for many years was SQL Server, and over there in SQL Server land, T-SQL, that's the name of their SQL variation, it's referred to as an apply. So very, very similar functionality. It's just the SQL standard refers to this as a lateral. What that means is this. We actually have 2 queries here. We have select from trucks, we call that the outer query. And whatever the result, so if you were to, in fact, let me do this. If I were to get rid of this, right, that's the query, select star from trucks. So it's going to, that table has 1 row per truck, and it's just going to give me, in fact, let me just do that. And plan it, there you go, 1 row per truck, order by truck descending. Now, for every row that is output from the outer query, it is joined laterally to this inner query. And you'll notice that I have, so there's the inner query, and I have this match right here where truck ID for this inner table matches t.truckID, which is my alias for the outer table. And so for every row from this outer query, we're going to run the inner query where the join makes sense, right? So where we have that where clause. And then we're going to spit out the results. And so we still expect 100 rows because there's, well, I'm sorry. We expect as many rows as we ultimately get. The inner query, if it's not limited, could spit out many rows, and that's not what we're looking for. So with a lateral join to get the last one, we always then order by, in this case, time, since we're talking about time, the most recent value. We order by time descending, and we limit it to 1. So truck ID 1, run this inner query, order the values by time, and only give me the top row. And tell you what I am going to do. I think with my internet problems, I forgot to prepare. So let me do that so we can talk about this. So let's go ahead and run that. And this takes 3 seconds, I think, 3-ish seconds. There we go. That took almost 6 seconds. There's only 100 trucks, and there's only 4 million rows in here. That seems like a pretty long time to get the most recent value. And you'll see the values are different, right? I order by truck ID. So we see that truck 105 is way back in November is the last time it reported. And we keep going down through. And then as we get closer, so currently, as we are talking, it is 12:33 for me. And so, sorry, I'll do this order by, here's what we'll do. We'll do order by time. And I don't know why I did that. We'll just say order by time. And I've explained analyze, which I didn't mean to do. There we go. Let me just do that one more time so you can see. So it's 12:33. And let's see what the most recent time for all of this stuff is. All right, so we know those first ones are going to be the ones that are oldest. I purposely deleted the data, and I'm not inserting any new data to them from that point forward. And then you'll see that it is, 12:34. We have some values that are back at 33. So every so often, there's a few of these that are not keeping pace with the others, but then they keep going forward. So that is how you do a lateral join. So I'm getting the value, but it's kind of slow. One of the reasons it's slow, and so now I'm going to do that explain analyze, and I've said this in other streams, always recommend when you're really trying to figure out why something is slow, and you'll get this from other places too, analyze and buffers. So buffers tells you all of your data is stored on what we call pages or blocks on disk. And in Postgres, that is an 8 kilobyte page, or 8 kilobit. I always get that wrong, kilobyte. And so the more pages you have to look at, the more time generally it's going to take, right? If it has to physically go examine more pages, whether it's in memory or off of disk, it's just going to take longer. And so I always recommend showing buffers. So let's go ahead and see what that looks like. Take a little drink while I'm waiting. All right, and so you'll see in this case, 4 million rows, 100 trucks, 105 trucks, and had to scan 12 million pages of data. It's a lot of pages. That's why it took so long. Now, why is that? I'm not going to get into exactly how to query tune here, except to say, we're getting rid of a lot of data. So we're basically scanning the entire index of every chunk and finding the matches and making sure that there's not a better value somewhere. And the reason is this. Let's see if I, did I forget that query? I had this, I thought ahead of time. Sorry, don't usually like to scan like this, and I apologize for that. Oh, I don't have it. Well, let me see if I can quickly, do I have it elsewhere? So I was just going to show you the reason is, oh, that's a shame. Let me see if I have that. one of these other places. Haha, there's my magical, there we go. Let's just copy this out because I thought I had this over here. So here's the reason. When I create that hyper table, we only create one index by default, right? So if you haven't done any other index tuning, we're going to make sure there's an index on the partitioned value, which is time in this case. So we can do time queries pretty efficiently. And the reason we need to do that is because features we add into the partitioning and the query plan and so forth. But I'm asking for the most recent value per truck. And so even though there's only 100 trucks, every truck has to now go through the entire table because there's no index to tell it. So it's literally scanning every single row and saying, is this truck ID 1? Yes. Is this value bigger than the last one? No. Go to the next one. So it's literally scanning over and over again. Really inefficient way of doing things. So instead, you should make sure you have the appropriate indexes on your table. Often it's the thing that you're trying to query against. So I'm going to create an index on truck ID and time descending. Again, because we want to find the most recent, it's the descending value, the top one of descending. So now when I do that, I have two indexes, one of which is a B tree by truck and time. And now let's run that same lateral again. And I'll do it without, well, no, let me first do explain analyze. And that was instantaneous, 27 milliseconds. You'll see that we went from, what was it, 12 million pages to boop, a total of about 450 pages of data. And that's because we could go to the index, find the most recent value for each truck ID, and then just go get the page itself and the values. So let's see what that looks like when we run it. And that's almost instantaneous. That was 8 milliseconds, and that's including drawing time and other things. So it's vitally important for any of these things to work well that you have the right indexes, even when you're doing something like a lateral join. So that's number one. And there's lots you can do here. You don't have to return everything. I could say, truck ID. In this case, I'd have to do t.truck ID. Maybe I just want to do time, latitude, longitude, and let me just get rid of that. So, oops, probably did. What did I? Oh, so lateral join works, and you're simply joining multiple tables together. The only other thing to add here is that there's I used inner lateral join, so this works just like inner and left, outer and so forth in a regular query. What this says is I'm going to run every row of the outer query. For every row, I'm going to run the inner query. If there's a match, return the value. If there's not a match, don't. So let's say that maybe a truck had never reported. It will not show up in the final result. I guess I could show you that by deleting data, but I won't based on time. So that's inner. If I did left join, I would get, every row from the outer one would still be returned, but the columns from the inner query, if there was no match, wouldn't. Left can always be a challenge because you're not constraining anything based on index then, right? So if it's a left join, if the index doesn't always match up, you end up getting scans because it's trying to make sure that there's correct value and so forth in there. So just be aware of that, be careful. And then last but not least, again, I can limit this a little bit further. If I were to say, where the make of the vehicle in this case, so the outer table, this where clause applies to the outer table, the outer query for the inner table. And you'll see that we'll get fewer results. This only has 14 rows. So there are 14 Ford trucks. And this is the last time they reported. And again, you'll see one or two of them are lagging behind the others. In this case, one of the Ford vehicles is lagging behind. And I'll, again, show you why in a second. All right, so that's that. So that is recursive join. So what is the second option? The second option, which you hear about often, is called recursive CTE. Now, I'll be honest, I like CTEs. They are very useful in a lot of ways, So again, CTE is a common table expression. You'll see that I actually, I think I used that up here. I shouldn't scroll up too far. My apologies. I did. So here's a CTE. With a CTE, you can create sub tables. So this was brands, models. This is how I populated that truck table. And it just makes a query more readable. I can then refer to those subqueries as tables and get values out of them. It's an easier way to kind of often do queries. Now, a recursive query, as I scroll down and make you seasick, a recursive query allows most databases support something like this. It allows you to start a query. So you basically have a first value. You then refer to that to the table itself with each row. So it's basically going to keep going until it runs out of values. And so in this case, I'm doing it based on this is the most recent time. That doesn't help me all that much because I'm not getting the ID. What I really should do, and I guess I did rewrite this below. In this case, this gets me the unique truck ID from the table. Now, why wouldn't you just do this from something like just doing a select distinct on? Well, the reason is in Postgres, and I'll show you by deleting this. I should have probably done these in the reverse order, but there's kind of a reason. A lot of people would say, hey, get me the most recent truck ID. This is one way to approach this. You could do a recursive you could do a lateral join based on something like a distinct. Let's say that metrics table had many trucks, tens of thousands of trucks. That loop could get slow because of the way the index, depending on the index you have. If you don't have an index just on the truck ID, that index is going to grow. So if I say truck ID in time, there's going to be an entry for every truck ID in time. And so as more and more data ends up in there, it's just going to get slower to go through it. A recursive CTE is a way to simulate jumping around in an index faster than doing the index scan. And so that might be one way you do that, but a lot of people try something like select truck ID, a distinct truck ID from this location and get me the most recent value, or even just select the just the truck ID itself. See, this is pretty slow. Even if I do just this, I'm just getting distinct truck ID. It's going through that table and getting 4 million rows to make sure that there's nothing missed basically per partition or through each table. It's just a problem with Postgres. It doesn't currently allow you something like what we call SkipScan. So it's not the best option yet, but you can do this with a recursive CTE, and it happens certainly a little bit more quickly. Oh, my apologies. I I got rid of that. So not always faster if you don't have the correct indexes. And so again, this is actually going to end up being pretty slow. So we're going to stop that. Let me put that index back on. And so even if you don't have Timescale installed, you can get very fast results with a recursive CTE. The problem is this can be tricky to write. And at this point, I'm just getting one column out. So now to get the time column as well, I have to then basically feed this into something that allows me to go find the right value. Now, the reason I'm showing it from the location table, not from the truck table, this is a different example, similar but different, is this is one way to say which, how do we want to show this? Let's say where time is greater than now minus, say, 1 week and interval. Oh, I didn't get this out. Okay. I'd have to set this up a little bit differently. But this is one way that you can say, like, hey, what hasn't reported? Gets tricky to show. But a lot of times, kind of like the company I used to work for, we needed to know what hasn't reported in the last 24 hours. And so you would say, hey, give me all of the IDs from the last 24 hours. I would set up, I would have to return the time as well and set that up appropriately. Um, and then, select from the other table where the IDs aren't in this list. So you often need that metrics table kind of meshed together. You want to see not just what's the most recent value, but also, has something happened recently? So recursive CTEs can be really beneficial. They're just more complicated to write, to be really honest with you. And even me in preparing this, I had to think for a minute or two and go find another example from another table to remind myself, okay, first I need to select this, unit with that thing. It gets complicated. And so that is an option though. And it's one that if you don't use Timescale or you don't have the correct indexes set up right now for whatever reason, it's an option to go find unique and recorded values over time. Ordered in the appropriate direction so you get what you need. And to show you, you can do it based on time. I think this was based on time. I was trying to show a couple other things there, but okay. So that is that. But what if you have Timescale installed? If you have Timescale installed, option number 3 is our SkipScan. And so the blog post on this will be in the description. And what this requires is that index. And so the way that a SkipScan works, it works on a B tree index only. Excuse me. Works on a B tree index. And if the order of your query, the order by matches an index, there's some nuance to it. I'm not going to lie. We are able to insert ourselves kind of into the query planner. And if there's a distinct on query and the thresholds of the statistics match, your statistics also have to be updated, which they should be. If you're doing appropriate Postgres activity, your indexes should be up to date. Then you can do a distinct on, and we will basically say, hey, wait a second. If there's a matching B tree index, we can probably find this faster. Now, there's only 100 IDs, and this table only has 4 million rows. There's a blog post we'll put in the link that just shows some of the performance we were able to get out of this. The title of the blog post is up to 8,000 times faster than Postgres. So even that the CTE will start to suffer some limitations. It's just harder. Honestly, it's harder to get the values out you want. So simply saying select distinct on, and here I can say star. So from truck location, I want to get the distinct most recent value, right? I'm ordering by time. So for every truck, get me the most recent distinct value. Very, very similar to sort by time descending limit 1, right? So very, very similar. I run this query, and again, that's almost instantaneous. That was 11 milliseconds. That got me every truck ID, even down to 105, the most recent value, and the timestamp. All right. And the way this works is we say, oh, you are ordering it based on that particular index. We can start at the index as soon as we find a match. We basically restart the scan not as if, we then say, okay, now go for the ID, truck ID greater than the one we just found. So we found truck ID 1, the most recent reading. Now find truck ID greater than 1, the most recent reading. Found that? Great. Start over. Now go truck greater than 2. Found it. Start over. We just keep that loop going. And that's how the distinct SkipScan works. A couple other databases do this. It can be really beneficial. Now, I will tell you, I didn't want to put 10 or 50,000 things in here. If you read the blog post, the more unique values you have, the slower it's going to get. With 100,000 or 500,000 unique trucks I would be tracking, this does slow down because we still have to work through we have to find the initial spot in the index. And that just takes planning time, and that's a Postgres, that's the way B trees work. So it does slow down over time, but it still is way easier to write. And for most situations, it's really fast and efficient to do. I can do other things here too. I can say, so often you would do this with paging. So I might say where truck ID, let's say I'm paging this 10 trucks at a time. So maybe it's greater than truck ID 20. So I'm going on to the third page, truck ID that, and then I would say, oops, limit 10. Oops, I gotta say limit it. So that gets me the next page of 10 items, and you'll see that it's ordered appropriately. And then if I were to click this, that would be a programmatic thing. Maybe your UI is paging 10 items or 100 items at a time. You can still do that with a distinct on, and that can be beneficial because we can more quickly jump to the appropriate part of the index and do that. So that is number 3. Now let's talk about number 4. Now this is one we don't, we touch on briefly in that example I was showing you here in this advanced analytics page. So we talk about it kind of at the bottom of this page. And again, in prepping for this stream, I realized we need to improve this just a little bit. The basic concept is this, and we have a number of users that are active in our Slack community that are doing this. This is a very typical application design. It's just the nature of databases needing to find a unique row in a sea of billions of rows. It's just hard. I mean, you can only go so fast. That is the reality of just the nature of data. Even some very fast, OLAP databases, very good databases like ClickHouse and others for specific features, really struggle at this specific thing. Find this one unique value for this one thing in the sea of all of this other data. And so what you can do is in a database like Postgres, in an OLTP database, is you can do something like create a specific table that just tracks the last reading or the last whatever you need to track. And as new data comes in, you insert that and update that one value in the other table. That table ends up being significantly smaller. Whoa, significantly smaller, right? So let's say you have 1 million devices. Well, if they're reporting every minute, what is that? That's 140 million rows a day or something like that. Maybe more than that. Is that 1 billion rows a day? Anyway, it's a lot of data. But if you have one table that only tracks 1 million rows, it's way faster to query that. SkipScan and other things can work through that table really quickly, all right, because there's so much less data. So what does that look like? So in something like Timescale, I'm just going to close this up here. We might create a table like this. Now, I didn't include the latitude and longitude. I probably should have for the example, so my apologies. But in this case, at least, I just wanted to know when was the last time that truck reported in. And I probably should have included. So again, my apologies. In preparing this, I didn't, and that was my fault. I should have latitude. I should probably put latitude and longitude in here. So I can update that for the next time I demo this. I created this, and we create that table. And then I created a trigger in Postgres. And I just said, hey, insert into that table the values truck ID and time from the other table. And I'll show you that in a second. Anytime there's a conflict on truck ID, so if there already is a truck ID column value in here, go ahead and update that last time value for me. Now, there's lots of ways you could do this. There needs to be constraints and some other stuff for the conflict to work. But in this case, it's the primary key in this table. I believe I guess I didn't set it to unique. I meant to. And so that should, if implemented appropriately, update the other table. And so then we took, this is a function, it's a trigger function. You have to tell some table to use that function when an action occurs. So in this case, we said create trigger, and we named it something different. Before insert or update, so before the row actually gets inserted into the truck location table as one option, you could also honestly do this after if you wanted to. Before it gets inserted, for every row that gets inserted, execute this function. Now, this is an example. Okay, quick warning. I should flash up the warning on the screen. This is an example on a small database. Depending on your database, how many items and how frequently this is happening. If you're inserting hundreds of thousands of rows every second, This might not be the best approach. There are other ways to use triggers and do things that might work a little bit better. Um, you might do something on a timed basis. Every few seconds, do a query and update it that way. So you're keeping some kind of log table. But in a lot of situations where you're not tracking sub-second data, things of that nature, this kind of trigger will generally work. And it ends up giving me, so let's see, let's do this. Let's say select count from truck log. I expect 100. And the reason not 105 is we get, remember, I'm only inserting data that timed. Oh, I guess I didn't have that in here. My apologies. I set up this other, or did I? Man, I'm so sorry. I thought I had it in the script. Oh, it's down below. That's where it is. Yeah, I had this little function. This is a procedure I wrote to just insert data once a minute for just 100 items. So the first 100. Remember, I wanted it to appear that trucks 101 through 105 just haven't reported for some period of time. And then I just added, again, add job is a great functionality of TimescaleDB. It's something that allows you to run a procedure on a timed basis. In this case, I'm running it every minute. And so every minute it's inserting 100 new values, except I do this little except thing. And so I randomly select 4 IDs out of 100 to not insert data for. Just trying to, again, create some randomness in this whole process. So as that happens, then I can look at this and you'll see that, as I expect, 4 items are not updating, right? So these 4 didn't update the last minute. But if I wait another, in fact, probably just about now, if I run that again, oops, still waiting. It's half past the minute. I'll probably get another 4 values that don't. So that's a really a decent way to do this too. Now, what's one other reason you might want to do that? Well, here's one other reason, and it's coming to mind. This will be the last thing I show in the stream. So let's go ahead and talk about compression real quick. I've done a few streams learning about and continuing to figure out compression at a deeper level myself. Let's just see if that updated because I'm curious. There we go. So my guess is probably, oh, I think I have up to 4. My apologies. So up to 4 items is how we wrote that function. So 3 of them didn't update the last minute. All right. So the one issue with compression, we like SkipScan. It's a great feature. We love things like order by descending, all good features. The one problem with those options, it's just the nature of how compression needs to happen within TimescaleDB. So if I say alter table, doing this on the fly, isn't this fun? Truck location set timescaledb.compress, say timescaledb.compress segment by equals truck ID. If I got that right, I did. So now let's say select show chunks, and we're going to say truck location. And here's what we're going to do. I'm going to say order by name. Thanks, Adam. I agree. Good vibes. So far, it's all working today. I'm going to say name descending. This is just a cheap trick that I do because I know chunk names are ordered. I say order by name descending. Oop, wait, what did I just do? And not name, my bad. Oh, sorry, I got to do this. Give an alias, order by I. All right, so now you can see the order descending. So now I'm going to do limit offset 1. All right, so that gets me everything but the most recent chunk. In fact, you know what I'm going to do 2, and here's why, because I don't know how far into this week the chunk is. So now I'm going to say compress. So for each row, For each row that comes out, so chunks, go ahead and compress it. So I should end up with 3 chunks that are compressed. Let's see if that happens. This shouldn't take too long. All right, so there's the 3 chunks. Now here's the one problem, and I'll probably have to go back. I'm going to copy this up here so that it's easier for me. Like I said, I just decided to do this. Always a good thing to do in a demo. Let me start with the lateral join. I'm just going to put this here and park it so I have it. So that lateral join before, actually still not too bad. So that's good. Let me do explain analyze on this one. That was about 500 milliseconds. So I don't know if you remember previously with the correct index, this was about like 12, 11 milliseconds. So it's still significantly slower. And surprised, there we go. Now, why did it get slower by compressing? The reason is you'll see that at some point here, we're going to get down and we're going to get a decompressed chunk. And the reason we got decompressed chunk, because obviously we compressed some values, and you'll notice that the index condition is on truck, right? So it can filter by truck ID, but it has to decompress that value internally, right? And so it's just going to be a little bit slower. As your table grows and more chunks happen, we're going to have to decompress every one of those chunks because you're not giving it a time constraint. It still has to go table, basically partition by partition. For this ID, is there any other value that's more recent than this one, right? It's just the planner isn't fully, because, how do I say this? Because those chunks now only have an index on truck ID, and again, go watch the compression videos. We talked about why that is. It was just a range on the values. And so there's no index. And so we still have to go chunk by chunk to see because there's no constraints. We know what values are within that chunk generally. It's just it's a problem without having any time constraints. So it's going to get slower. And so that might be a reason the larger your table gets, whether it's a recursive query or, and this is the real kicker, I'm going to skip down past the recursive stuff to our distinct on. Even distinct, this is probably going to be pretty fast. That wasn't too bad. That was 800 and some milliseconds. But you'll see that it still had to go, even though we have these, we said truck ID is greater than X, limit by 10. There's just a lot of planning that has to go into, like, it doesn't know exactly, every single row and where it is, and there's no index matching this exact thing. Now that we've compressed the data, it just has to do more work because the index is gone that the distinct needed. And so that's one surprise that a lot of people have. When you compress data, we get rid of the indexes. We only keep indexes for your segment by columns. And again, go read the docs, look at the videos. We explain all that, why that is. So we end up doing a lot of extra work. And it's just going to end up being slower. I don't know if you remember this query, after we added the index, I think only touched, it's like 450 pages as opposed to 12 million. And we're back up to, thousands and thousands of pages, and it had to write stuff out to disk to sort and do all kinds of other stuff. So that would be one other reason. Now, even though I've compressed it, this should still be trucking down here. So if I select, this is still really fast and it's keeping pace, right? So I'm at, so I'm at 104 as we go, and 105 and so forth. So that could be a reason to do that last option. You'll have to look at your specific schema. You'll have to figure out what is the best way to approach that. And again, if you have really high throughput, you might need to approach it differently. In fact, let me make one other quick comment here. Love how my brain works. Here's the last comment, last tip for you. In Postgres, and this goes into theory. I probably should maybe do a separate video or talk on this, or even a little blog post. When I created this table, all right, now and in fact, I had no, there's no index on this. So that was kind of bad for my part too. I should put an index here. But this is a Well, there's primary key, so there's going to be an index for that. Should be, let's go see what's on here. Truck. All right, there you go. So there's our unique index. So there is an index on truck ID. The problem is the way that indexes work in B-tree is in Postgres, when I insert a new value, I don't update the row that's there. So Postgres uses what's called MVCC, which always inserts a new row with the newer values, marks the old row as basically old or deprecated, and eventually it will be removed. So we can always be reading data at the right transaction level, and it just works. The problem is if you have a table like this, a logging table that is always just storing the most recent value, you can get into a table bloat situation, particularly with high throughput data. So I'm going to scroll down here and talk about this. So, excuse me, going back to this, we had hundreds of thousands of these, reporting anywhere from a minute or less to 5 minutes or 10 minutes. Lots and lots of unique values, maybe 30 unique values per device or more. I don't honestly remember at this point. Our metrics table that tracked the most recent value, the last time the thing reported, and we tracked some of those values, hundreds of thousands of rows, and updated across hundreds of thousands of devices. There was an update statement happening on that table multiple times a second, right? So unless vacuum analyze is happening appropriately, auto vacuum, a whole different tuning discussion, you end up with what's called table bloat because we're inserting new rows faster than Postgres can clean them up. And imagine I have a page of data with many rows on it. I'm going to do another talk on this. That's what's going to happen. Many rows on it. I can't update this row for truck 1, right? It reports in, and there's no space left on this page. If there's no space left on this page, now I have to create a new page, insert that one row, and generally, most of the time, oh, I had my hand in front of there. Hope you heard me. Most of the time, Postgres will put a pointer to the new row while it's waiting for this row to be deleted. That ends up with what we call table bloat. So if you end up doing this logging table, my recommendation to you is to take advantage of one other feature of Postgres, and that is called fill factor. It's been long enough that I didn't plan to do this. It came to mind. So what you can do, I'm just going to look it up because I'll be honest, I forget exactly. Postgres fill factor. My apologies. So by default, it's 100. So it tries to fill, I've talked about this before. Looked at this before. Let's go see what we have here. Let's see, fill. All right. Great, great, great. Is there any, there we go. So, so you can say with fill factor. All right. So I bet I can alter the table. Let's see if I can. Alter table truck log. Is it with fill factor? Yes, with. And it's just, yeah, I don't think this is going to work with, but we're going to see if it will let me. We'll say 90. Yeah, it doesn't like that. Maybe I can say set. Oh, there you go. Set fill factor. That makes complete sense. So what this means is this. Now, this only happens from every time that you vacuum or analyze the indexes, basically redo the indexes. Now it will only fill each page 90% and leave some room on the page so that each update can still write to that page. We don't have to create more. We're not growing the index. And as long as your vacuuming is keeping up, you'll keep a much smaller index over time. So in fact, I noticed this link. Let me go back to that link. I think this is one I've looked at previously. It's purple, so I definitely have. This is a very good write-up by Cybertech, just showing this. They went through a couple examples. I remember this thing. Fill factor 90, 80, 70%. Their basic take was, hey, probably 80 to 90% is good enough for a high frequency table. You're not going to get much more benefit other than that. So your initial space will take a little bit more, but then it will be maintained better over time. And here's why that's important. The smaller you keep your index, the fewer pages we have to go through, and ta-da, the faster your query is going to end up being. Right? If the Postgres has to work through fewer pages, generally you're going to get better performance. So if you end up doing a logging table like this, consider playing with fill factor, particularly if it's high frequency and you have a lot of things. So if you're going to end up with tens of thousands or hundreds of thousands of rows updated, pretty consistently, it's always a matter of how quickly Vacuum Analyze can keep up with your database. All right, and your updates and so forth. Wow, there you go. That was just over an hour, almost exactly an hour once I chop off the 5-minute thing. So I get a little bit better thinking through this stuff. If you have other questions, let me know. So I'll put a couple things up here for those that made it to the end. Good work. I'm proud of you. Obviously, go to docs.timescale.com. Everything I showed today will do that. Let me hide my screen here. And please come check out Slack. So we have slack.timescale.com. You can find me. You can find other developer advocates that you've seen streaming recently, like Miranda. David's in there. Tilla's in there. Number of engineers will show up from time to time, many of which have helped maintain and create these features. So come ask us. We'll do our best. But there's at least 4 ways that you can go about finding the most recent value within Postgres and TimescaleDB using some of our features as well. I hope that was helpful and look forward to hearing from you how we can show this a little bit better next time. Thanks so much. Have a great week. And we won't see you until after the US holidays. So for me, that means Christmas. For you, that means maybe something else. Have a great end of the year. Happy New Year. And we'll hopefully see you in the new year and continue to work our way out of 2020, right? All right. Great to see everyone. Take care.